Hello everyone. So in the last video we talked about black holes. We talked about the process of star death and which stars can become black holes, which ones can't. We talked about the concept of density and how that's important in determining which stars can become black holes, and really just how density is a very important characteristic of black holes. And we got into escape velocity. So I'll remind you that's the speed at which an object can escape, quote unquote, the gravitational pull of another object. And then we talked about how that relates to black holes. So we said that around the vicinity of some density of matter, the escape speed around this black hole needs to equal or exceed the speed of light. So what I've drawn here, this circle in the middle is our black hole, and then this dashed line can be referred to as the starting point of the event horizon, also known as the point of no return. You've probably heard that, like I mentioned before, light can never escape a black hole, and that's true, at least once it reaches this boundary. So this is my light approaching the black hole, and once it gets to this curved line here, this boundary, the escape speed is going to be equal to the speed of light. So technically it can't escape it at this point, but once it gets past this point, not even light can escape it. And that's why black holes appear so dark, because it's consuming all of the light that passes this point. So what if we wanted to calculate the size of the event horizon? When people talk about the size of black holes, that's what they're referring to. They're referring to the size of the event horizon. And that's what I've drawn right here with this blue line. This is known as the Schwarzschild radius. I know it's kind of a weird name, but it is how it is. And if we wanted to derive an equation for this, we can actually use the escape velocity formula and get a new equation. So you'll recall that the formula for escape speed is equal to the square root of 2 times the gravitational constant times the mass you're trying to escape from, divided by the distance between their centers of mass. So we've already determined that at the edge of the event horizon, the escape speed is equal to the speed of light. And if I haven't already said this, the speed of light is the variable c. So, since we know that, we can say, okay, well, my escape speed is the speed of light, so that's what I do know, but I want to know what distance from the black hole is my escape speed the speed of light, because then we can figure out the distance between that point and the black hole, also known as the size of the event horizon. So we can change this r right here and say this is r sub s. This is the Schwarzschild radius that we're solving for, since our escape velocity equals the speed of light. So we can say c equals the square root of 2 times gm over rs. And we want to solve for rs because we're trying to make a new equation that solves for the Schwarzschild radius. So we can square both sides, and we can say c squared equals 2 times gm divided by rs. And we can actually just switch these. In doing so, we'll find that the Schwarzschild radius equals 2 times gm divided by c squared. So how is this relevant to this video? Well, the recent picture that's been going around of the first ever picture of the black hole, we can use some information we know about it already, and using that information we can find the Schwarzschild radius, which is not something you would find in any news articles because frankly no one cares, but we care because it's cool information. So if you don't know already, the black hole is actually at the center of the galaxy Messier 87, and if you've seen the picture, you'll probably notice this cloud of bright gas circling the black hole. So the black hole is like this blue circle in the middle, and you'll notice it kind of spiraling around, and it just kind of looks like a donut. So something I haven't talked about yet is this area right here where the gas is spinning. That's called the accretion disk. And so I'm doing this just to basically help you better understand the picture, and we can also use some information that we've talked about in the last video. So right here we can, this is 3D, it's more like a dome that surrounds the black hole, but we can say that this edge right here is the event horizon. Like we said, it's just where light is not escaping it, and it's more coming out to you versus on the side, but this is not 3D, so I can't show you that. Another thing that we can figure out is that the star that formed this black hole had to have been greater than 3 solar masses, because as we talked about, when a star dies, one of 3 things can happen. It could become a white dwarf, it could become a neutron star, or it could become a black hole. And for it to become a black hole, the mass of its core would have to be greater than 3 times the mass of our sun. Another thing about this black hole is that it's classified as a supermassive black hole, so that just means it's greater than 1 million solar masses, which is obviously greater than 3. So the next thing we're going to do, and actually our final thing for this video and for this series, we're going to calculate the Schwarzschild radius, or the size of the event horizon of this black hole. And really the only thing that we need to do this is we need the mass of the black hole, which I found online, and we already know the speed of light, we know the gravitational constant, and so we're good to calculate it. So that's what we'll do next. So I'm just going to go ahead and explain what I have here. I know it looks really crazy, but all I did was just plug in the numbers that we know. So our Schwarzschild radius is going to equal 2 times g, our gravitational constant, and so I just filled that in for this parentheses, and then we're going to multiply that by the mass of our black hole. So that's going to be 6.5 billion solar masses, so 1.99 times 10 to the 30th kilograms is the mass of our sun. Fun fact. And then I just divided that by the speed of light squared. And I forgot to write something here. It's meters squared per second squared. So when you square something, you also square its units. So the next thing we're going to do is cancel out some units so that we can make this equation look a little better. So we have 2 meters squared right here. So we can cancel it out up here and down here. We can't do anything with our second squared. And I know this is kind of hard to see, but the kilogram squared is on the denominator of this unit, and just our kilogram to the first power is on the numerator of this parentheses right here. So essentially what we're doing is kilogram over kilogram squared. So when we do that, we can get rid of this and get rid of that exponent. And so that's what we're going to do up here. We're going to get rid of that and get rid of this. And that's all the canceling we can do right now. So now we just need to rewrite the equation. Alright, so now our equation looks a little more friendly. So what I did was I multiplied our gravitational constant, our g, by 2. So that's what this is. And then I multiplied our 6.5 times 10 to the 9th solar masses times the mass of our sun. And then I just removed all the units that we canceled out. So the next step here would be to multiply this number by this number. And then once we do that, we would divide what we get there by this number. And I'm just going to go ahead and write what that is, and then we're going to cancel out some more units. So when we do all that multiplying and dividing, we end up getting this number right here. So if you're wondering how I'm doing these calculations, a few rules when you're working with exponents. So say you have, I'm just going to draw a line right here. Say you have 5 times 10 to the second. And then you're multiplying that by 6 times 10 to the second. So what you're going to do is just multiply these front numbers as you normally would. So 5 times 6 is 30. And then you're going to do that times 10. Make sure you have the same base here. And you just add the exponents. So 30 times 10 to the fourth. So whenever I'm multiplying the numbers, that's what I'm doing. And then when I'm dividing, so say you were doing the same problem, you're doing 5 times 10 to the second divided by, I don't know, 2.5 times 10 to the second. So when you're doing this, you're just going to do the same thing. You're going to divide these. So then you're going to get 2 times, and then when you're dealing with your exponents, you're going to subtract them in this case instead of adding them. So 2 minus 2 is 0, 10 to the 0 is 1, so your answer is 2. Those are really the only 2 rules that you need to understand in order to do these equations. So let's move back to what we were doing. So after doing all those calculations, you get this number up here, but we still need to deal with our units. So one thing we can do is convert our newtons into its other form, which is kilogram meter per second squared. You can probably see why they abbreviate it. One rule you might remember about dividing a number by a fraction is keep, change, flip. And so that's what we're going to do to these other units right here. So essentially what we're doing is 1 divided by kilogram per second squared. So you'll remember that what we do is we keep the first number. So we're going to do this over here, 1 times, you change the sign, so that's keep, change, and then you flip your fraction on the bottom. So you're going to get second squared over 1 kilogram. And so that's how we can make this fraction a little simpler. And so we can move this over here, so that's the same as kilogram meter per second squared times second squared over 1 kilogram. And then we can cancel out our kilograms, cancel out our second squared. And so what we're left with is 19.17 times 10 to the 12th meters. We can convert our final answer into kilometers, so there are 1,000 meters in 1 kilometer. We can change our exponent to 10 to the 4th because we're subtracting 1,000. And then if we wanted to expand this, we can move our decimal 4 places to the right. So we can do 2 here, and then add 2 more zeros at the end. So our final answer is 191,700 kilometers. And this is the Schwarzschild radius of the black hole at the center of Messier 87. To conclude this video for today, I'm going to give a quote from Stephen Hawking. He says, "We are just an advanced breed of monkeys on a minor planet of a very average star, but we can understand the universe. That makes us something very special." Thank you for watching, and I hope you enjoyed.